Hello. Last time we talked about the convolution theorem, and the convolution theorem states that if you take the Fourier transform of the convolution of two vectors, then it is equal to the the component-wise multiplication of the Fourier transform of the two vectors. So now today we'll prove the convolution theorem. So the statement is on your screen. And let's try to prove this. Okay, so the proof is the following. So the first step in the proof is to note the following thing. So if I have the jth column of a Fourier transform matrix, and you take the dot-wise product of that with the kth column, then this is equal to the j plus kth column, right? Where j and k are running from 0 to n minus 1, right? And of course, this is we are always dealing with a 2n dimensional. So this is a 2n dimensional Fourier matrix, right? So this is quite straightforward. So the dot product, so if I look at f, so what we need to show is that f star j cross f star k, the teeth element is equal to f star j plus kth teeth element. But that's quite straightforward since this is jt times epsilon, eta kt, which is equal to, the left-hand side is this, which is equal to j plus k, which is equal to f star of j plus k. Okay. So that's so which means that if I take the jth column of a Fourier 2n cross 2n Fourier matrix and take the component-wise multiplication with the kth column, then I will get the j plus kth column. Okay. All right. So moving on. Now just let's write down. So if I have the Fourier transform of a hat, right? So I have a 2n cross 2n matrix, right? And I'm acting upon it by this vector a hat, which consists of components alpha naught, alpha n minus 1, and then there are zeros padded over here, right? And so I can write this Fourier matrix as a set of columns. F0, F star 0 will be the 0th column, and so on. And there'll be 2n columns like that. So, and this is equal to summation k is equal to 0 to n minus 1 alpha k f star k. Now, why are they only n terms over here? Because of the padded zeros. Okay, so when I want to multiply a matrix with a vector, then from basic linear algebra, I know that this is equal to this component of the vector multiplied by this column plus the second component multiplied by the second column and so on. But here it's a 2n cross 2n matrix, but only n terms are there in this on the right hand side. That's because the remaining n terms in the column vector are equal to 0. Okay, so let me just erase this. All right, then of course we have similarly hat is equal to Fourier transform applied to b hat is similarly k equal to 0 to n minus 1 beta k f star of k, and f of a hat convolution b hat. By definition, we get this to be k equal to 0 to a b k of f star k. And this will be going from this to 2n minus 2, right? Okay, that's all just by definition. Now, if I take f a hat, so this will always denote component-wise multiplication. Then what do you get? You get this summation k equal to 0 to n minus 1 alpha k f star k multiplied, this is dot-wise multiplication, summation k equal to 0 to n minus 1 beta k f star of k. Okay, so okay, if I do this dot-wise multiplication, I can use the fact that f star of j into f star of k is equal to f star of j plus k. And this is essentially just polynomial multiplication, right? So you get summation k equal to 0 to 2n minus 2. Then summation j equal to 0 to k, right? Then, of course, it will be alpha j times beta k minus j. Okay. And then it will be f star of j cross f star of k minus j, which will just be f star of k because of this fact. So we get equal to f a hat cross f b hat will be equal to summation k equal to 0 to 2n minus 2. And I can write this as a convolution b kth component f star of k, which is also equal to f of a convolution b. Okay, so that is the proof of the convolution theorem.